Hi, I thought I would talk to you a little bit about convergence proofs for stationary methods. So in class we looked at the Jacobi method, we looked at Gauss-Seidel, the successive over-relaxation SOR, and in the homework you're talking about a general convergence proof for such methods. We sometimes call them stationary methods, but I thought to just show you three examples of convergence proofs. All of which use just a slightly different approach. So it's really nice to have a look at this, and hopefully you'll get some inspiration. So we're going to be looking at the Jacobi method for row strictly diagonally dominant matrices A. And then we'll see that we can actually do this if we choose the norm for which we want to show convergence smartly. And then we'll do it for column strictly diagonally dominant matrix A, and then later for Gauss-Seidel for symmetric positive definite matrix A. And in that last case, number 3, we'll actually be using the spectral radius smaller than 1 convergence criterion. But in the first two, we'll use different norms. So let's start with number 1 for a row strictly diagonally dominant matrix A. Okay, so let's see. We have an n by n matrix A. Oops. Okay, we write A as L plus D plus U, just like we did in class. And then we take M is equal to D, right? We had N is equal to minus L plus U. And as a result of it, we have our iteration matrix G, which is M inverse N. And that is equal to minus D inverse times L plus U. But if you look at this, then we can also write this as the identity minus the inverse of D times A. And this is actually the one that we're going to be using in this proof here. Now, one thing to note is that this G has a 0 diagonal. All right. So if you look at this here, that's really easy to see. Okay, so note that diag of G is 0. Okay, and so that means that GII is 0. And we can also see that the off-diagonal elements, Gij, are equal to minus Aij divided by Aii. Okay? Now, what does it mean to have a strictly row diagonally dominant matrix? So, A is row strictly diagonally dominant, and out of this follows that we have a big fat diagonal. So the absolute value of Aii, that diagonal element, is actually larger than the sum of the absolute values of all the other elements in that row. So we go from J is 1 to N, and we add all of these guys up, but not for J equal to I, then we have this inequality hold. Okay, so we call that star. Okay. Now, to show convergence here, we choose the infinity norm for G. And you may wonder, well, how do you know to choose this? But the infinity norm is the maximum row sum. And so if I have a row strictly diagonally dominant matrix, it makes a lot of sense to start thinking about row sum. So for G, this is equal to the max of all the rows. So for I between 0 and N of the sum over the whole row, J is 1 to N of Gij, like this. Okay. Now, knowing what A looks like or G looks like in terms of A, which was given here, like this, we can readily see that this is equal to the max from for overall the eyes of this thing here, I, and this is for j equal 1 to n with j not equal to I. So we've basically just used the fact, we know exactly what this g looks like, and then if we now put in star, we immediately see that this will be smaller than 1. Okay, so what we have here is that we can find a norm, in this case g infinity, and that norm for this iteration matrix is smaller than 1, and that is sufficient proof for convergence. It's not necessary, and you see this in the homework, that a necessary and sufficient condition is that the spectral radius is smaller than 1. If this infinity norm is smaller than 1, then we also have that the spectral radius is smaller than 1. And you've shown this in your homework as well, because you know the spectral radius is the smallest norm. Okay, so this was for a row strictly diagonally dominant matrix. What if A is column strictly diagonally dominant? Okay, so I'm working on my iPad here. I'm not very good at writing on my iPad yet, so I tend to abbreviate things so that I don't have to write that much. Okay, so if we have column strict diagonal dominance, that means that the diagonal element, now we call them A, JJ, is bigger than the sum over or the absolute value of all the other elements in the column. So in this case, we go from I is 1 to n, with I not equal to j. Okay, now it is clear that we cannot use the infinity norm, because that was for a maximum row sum, and so we will be inspired to use the one norm of a matrix, because that is the maximum column sum. But we have to be a little bit careful, because if we try to use the one norm for this matrix, then we actually don't get a very easy proof. In fact, what we'd like to do is look at a weighted norm, a weighted one norm, and we weigh it by the diagonal d. And you will see that if we do that, everything turns out to just be a little bit simpler. So it's interesting to look at this proof, because we have a completely different type of norm. We don't look at the spectral radius, we don't look at the infinity norm of the one norm, but actually a weighted one norm. And the norm that we're going to be looking at is this one here. And we just notate that with a subscript d, and this is equal to x weighted by d, and then the one norm. So this is the norm that we're going to be looking at. Okay, so we look at GG like this, then that would be the max over all x not equal to 0 of g of x d divided by xd. And now we'll just go and manipulate this a little bit. We'll play. So this is the max over all x not equal to 0 of dgx one norm, right, divided by dx one norm, like this. And we can write this again a little bit different. That is the max of x not equal to 0. And now we look at dg as before, but now we put in there an identity, d inverse times d, x one norm, divided by dx. And the reason why I'm trying to do this here is because right here we have dx, and I'd like to somehow get a dx also in the top part. So this is what I've done now. And so now we're really interested actually in the behavior of this matrix here, dg the inverse. So let's have a look at that and see what we can do with dg the inverse. Okay, so with dg the inverse, okay, that would be equal to g. Now g was the identity minus the inverse a. And this goes to the inverse here. So if you look at this, this would actually be I minus a the inverse, like this. Okay, so we use this and we plug that into that norm. So we get g of d right here is equal to the max over all x is not equal to 0, like so. And then here we have I minus a the inverse dx, and that was the one norm, divided by dx, the one norm. Okay, so now we've isolated these dx's, and so why don't we just call them w's? So this would be the same as the max over all w's not equal to 0 of I minus a the inverse w one norm divided by w one norm. Okay, right? But this of course is just the definition of the one norm of I minus a the inverse. Okay, and that is the maximum column sum of this matrix I minus a the inverse. So this is equal to the max right, over all columns. Here, I have to look there for a second. It's the sum from I is 1 to n and I not equal to j of ijj divided by, oh sorry, here this should be an I, and here we get ijj. Okay, but we know because A is column strictly diagonally dominant that this is smaller than 1, and we found our proof. So see, in this case here, you probably would have been tempted to use the column sum right from the start. If you've tried that, if you try this, then it just gets a little bit hairy with the d's. That's why we do the weighting. So it takes a little bit longer, but still a pretty nice proof. Okay, so now let's go to my favorite proof, and this is number 3. So now